Okay, so the basic goal of this series of lectures is to give an introduction to analytic geometry, but essentially what I have in mind is to introduce to fundamental methods of algebraic geometry. So the main goal is to study, say, algebraic varieties, but using analytic methods. So in many ways, you can relate the algebraic properties to differential geometry and to topological concepts or cohomology concepts. That is the general goal. Today I will concentrate on very basic stuff. So essentially, chapter 1 will be an introduction to holomorphic functions of several variables. So most of you probably are familiar already with holomorphic functions of one variable, but it turns out that properties of functions of several variables are more involved, and so I will try to explain the differences. So first, basic definitions. So let us start with an open subset, capital omega of c to the n. N will always be, in this series of lectures, the dimension, complex dimension. If it's real, it will be Rn, and if it's complex, it will be C. So let omega be an open subset. Then you have the following theorem and definition. So let f be a complex function defined on omega into complex numbers. Then the following are equivalent. TFEA abbreviation for the following are equivalent in English. First property, F can be is C analytic. Quotes. So this means, i.e., which, well, you're familiar with this, it means id as in Latin. Okay, C analytic, namely for every point z0 in omega, there exists a convergent power series representing f in a neighborhood of z0, and more explicitly in an open Polynomial disk, a small open Polynomial disk. So usually we know this by dz0r, which it's a product in each coordinate of disks. Okay, so from j equal 1 to n of dz0j rj, where you write z as c01 c0n,
and this is a multi-radius, so R is R1, Rn. And this means that you can write f of z equal sum over all multi-indices alpha in capital N to small a of a alpha z minus z0 to the alpha. So this is multi-index notation. So multi-index notation, you write z to the alpha. So alpha is an n tuple, alpha 1, alpha n, and z to the alpha means z1 alpha 1, z2 alpha 2, zn alpha n. And of course the coefficients here, the coefficients a alpha of course depend, a alpha depend on z0. So a alpha of course depend on the central point. And the polydisk, of course, well, to make sense, should be contained in let's say capital omega. So this is the C analyticity property. Second, f is actually a C differentiable. But I insist that it's over complex numbers, so it means differentiability, but with C linearity of the differential. So it means that for every point there exists a neighborhood capital B. This is zero. On which you can write f of z equal f of z0 plus L dot z minus z0 plus little o of z minus z0. So here I need any norm, well, you are on a finite dimensional space, you're on Cn, so any norm. So little o here, so small compared to the norm. And L, well, that's important. It's a complex linear map from Cn into C. So it should be not just R linear, but C linear. Okay, second property. Third property. F is continuous on omega. And separately holomorphic in the sense you know in each variable. For each j, if you consider the map depending on the j variable, maps to, so you fix the other components. Z0, 1, Z0, j minus 1, Zj, Z0, j plus 1, Zn. Is holomorphic in Zj when you fix the other components.
So this is referred to as being separate holomorphicity. So F is said to be separately holomorphic. And now, fourth property, you can actually represent F by the Cauchy formula. So you have the Cauchy formula. Cauchy formula holds. So it means that for every closed polydisk, Z0R contained in omega, then you can represent F as F of Z equals 1/2 times an integral over what is called the distinguished boundary of the polydisk. The distinguished boundary is not the boundary, it's the product of the boundaries of the circuit. Okay, so it's the product of the circuits. The symbol is del is equal to boundary of EZ0J. And then you integrate F of W. Well, you take the product of Wj minus Zj times dw1 dw4. So it's actually a multiple integral, so you integrate with respect to, well, if you want, it's just circles. So you can, you can just set Wj is equal to Z0J plus, well, you are in the circle of radius Rj, so Rj exponential I theta j, and of course you have only the angle varies. Theta j is, say, 0.25, and then of course dwj is simply I Rj exponential I theta j theta j. So just the analog of the usual Cauchy formula, but there are several examples. And then, if any of these equivalent properties are satisfied, well, you say that F is holomorphic in definition. Then says that F is holomorphic in omega, and notation script O of omega is the set of all holomorphic functions on omega. All F that are holomorphic on the omega. So it's easy to see, for instance, from the differentiability property, that this is going to be a C algebra. So you add or multiply holomorphic functions, it's going to be, again, holomorphic functions. So this is a C algebra. Okay, so now I'm going to briefly prove the equivalence of these properties. Okay, so first you have to know the standard properties of power series. So it works essentially as in the case of one variable. So if it's convergent, certainly proof. So it's definitely very easy that first property is very strong and implies proof the others. Well, implies easily 2, for instance, because convergence implies convergence. So assume 1. And convergence implies that you have a bound on, well, at least because you have convergence, if you take the absolute value of the modulus of A alpha times Rj, and you have to subtract a little bit of slightly smaller, so take Rj minus epsilon. Well, I write like this to the alpha. So actually, this means R1 minus epsilon times alpha 1, etc. Notation. So this is going to be bounded. It's going to be bounded because simply if you fix a point in the polydisk, it's convergent, and if your series is convergent, then of course the terms have to be bounded. Okay. So for some bound. And then it works as in the case of one variable. If you have a power series that is satisfies this property, it is of course normally convergent, uniformly convergent on every smaller polydisk. I don't give all details, so it works exactly as in the case of one variable. So this implies then the power series, although it is multivariable, power series converges uniformly on say D0 R minus 2 epsilon, simply because well, the ratio will be strictly less than some constant less than 1. So we'll have Z minus Z0 to the alpha divided by R minus epsilon to the alpha. Absolute value is going to be less than something like 1 minus delta to the total length of alpha. So the total length of alpha is alpha 1 plus n. Okay, something like this, and this implies uniform convergence. And then also it's true for all derivatives. Okay, and well, if you differentiate with respect to, you can differentiate with respect to any variable. So you have del f over del Cj. You can differentiate. So you're going to get. Well, the formula will be sum over alpha of component alpha j times A alpha z minus z0 alpha, and then minus delta j here, where delta j is the interval 0, 0, 0, 1. Okay, so you lose one factor in the component Cj. But then again, this is going to be uniformly convergent because you have an exponential and this is negligible exponential. So I give you the details of it. Exactly as in one variable. And then you easily infer that it is C differential. Okay, so this implies it's even C infinity. You can indefinitely take derivative of C. One has
complex derivatives at any rate. And therefore, two instances. And it is essentially trivial that 2 implies 3, because of course differentiability implies continuity, and then of course you can take derivatives in each direction, and therefore 2 implies 3. It's clear. Okay, so now I'm proving that 3 implies 4. This you can easily do by induction on n. So actually, you know that this is true for n equal 1. This is a standard Cauchy formula. So assume that you already know the result for dimension n minus 1. And then I apply the formula. So here the product is from j equal 1 to n. But now I apply the formula by fixing the last coordinate. So I just consider z1, zn minus 1 maps to f of z1, zn minus 1, and then wn. So wn is fixed. Okay, so I apply the formula to this, so I get that f of z1, zn minus 1 wn is 1 over 2 pi I to n minus 1 integral for w1 wn minus 1 in the polydisk of dimension n minus 1 of f of the same thing, except that I divide over the product of wj minus cj from 1 to n minus 1 only, and I integrate only with respect to dw1 dw n minus 1. Okay, but then now it turns out that this is going to be, by assumption, it's you have a holomorphic function with respect to wn, and by standard theorems on derivation under the integral sign, this is going to be a holomorphic with respect to wn on both sides. So this is holomorphic with respect to wn on both sides. And you assume that your z is in the interior, so z doesn't touch the boundary, so the denominator actually does not vanish, and so you have something like this. So you have the polydisk. So the product of this is going to be here. So I can draw for only two variables, say z1, z2. So the distinguished boundary actually is the product of the boundary. So it's not the topological boundary. Okay.
Okay, the topological boundary is more complicated at this point. So you integrate on the product of the disks, but then you take a point that is inside, so it is definitely at some distance. So this denominator is bounded away from 0. It's bounded away from 0, and therefore you have a uniform bound, and the function is continuous. So you have a uniform bound, and then you can also differentiate with respect to Wn. And you can apply derivation under the integral sign. So no problem there. And now you just apply again the Cauchy formula, but now you apply Cauchy formula with respect to variable Wn, and you apply the Fubini theorem, and then you will get the formula for dimension. So just apply now. Just apply Cauchy formula. With respect to the variable and you're not, and apply food. Not a complicated version of Fubini, it's just Fubini for continuous motion. Okay, and now we need the last part. The last part is 4 goes back to 1. And then it's completely standard. Well, you have this product, so let us just consider one factor. So of course here Wj in my notation is on the boundary, so Wj is absolute value Rj, but Zj is smaller. So Zj is inside the polydisk, so it's less than Rj. So what you are doing is that you write this as 1 over Wj times 1 over 1 minus Zj over Wj, and then you expand this by usual expansion of 1 over 1 minus u, so you write this as sum, and I'm going to use index alpha j n of zj to the alpha j divided by wj to the alpha j plus 1, which is this one. And now you take the product of this, so you get that the product of 1 over wj minus zj is the sum, and this is of course absolutely convergent. And then you take the product of the series, so you get a sum over all the multi-indices, alpha 1, alpha n, or n to the n, of the product of these things. So z to the alpha divided by w to the, alpha plus fat 1. So fat 1 is just 1 on. Okay, and then you plug this here, and what you get is, so this gives, by commuting, you have an absolutely convergent series, so you can commute integration, summation, and this gives f of z is equal to the sum of a alpha z alpha,
A alpha is 1 over 2 pi I to the n, very similar to what we have in one variable, times the interval for w in the distinguished boundary of what it is, times f of w divided by w alpha plus fat 1 dw1 dw. And therefore, your function is CNN. So the theorems. Okay.
A remark is that in fact you have an even stronger property which I will not prove, but it turns out that holomorphic functions are extremely rigid, even in several variables. So you can even drop the continuity assumption. If you have a so-called Hartog's theorem that was proved around 1900, that if you have a function that is separately holomorphic, even without assuming continuous, then this implies holomorphic. It's a little bit deeper, not extremely difficult. I will not do it. It's certainly done in my book somewhere. Theorem. The proof uses a little bit of potential theory of observable functions, so you need more material. So in fact, just separately holomorphic, separate holomorphicity without continuity. So even without assuming f continuous. Implies f holomorphic. Okay, so now I come to the topology of omega. So, is everybody here familiar with what is a locally convex topological vector space? What is a precious space? Sorry?
Not really.
Not really. Okay. So the topology is defined by a family of semi-norms. When you have a norm space, you have a norm. Okay? And the norm is used to define the distance. Used to define the walls and so on. Here you don't have a unique norm. You have a lot of norms, and actually as semi-norms. Okay, so you fix, take K, and K in omega be a compact subset. And then you define pk of f is just the supremum for z in the compact subset k of absolute value f of z. Of course, it's also maximum because f is continuous, so the supremum is big. So this is a semi-norm. So by definition, what is a semi-norm? So you have say a K vector space So the field I'm going to use is either real numbers or complex numbers. You can also consider topological vector spaces over valued fields, but I will not need that here. So K here is R for C. And then the semi-norm is just the same as the norm, except that you don't require necessarily that the norm, that it's separated. So the semi-norm, it's a map from E into the positive real numbers. So X maps to P of X, which is homogeneous with respect to multiplication by scalars for every lambda in the field, and P of lambda X is absolute value of lambda P of X. And then you have the triangle inequality that for every vectors P of X plus Y is less than P of X plus P of Y. But then you don't necessarily require that that P of X is 0 implies X 0. You forget that. Don't necessarily assume separation. Separation means that P of X 0 would imply X. Okay, and then when you have a norm space, you have a unique norm. Okay, but then you can consider any family of semi-norms. So suppose you are given an arbitrary family P alpha for some set I of semi-norms. Then I'm going to define the topology, vector space topology, as follows. So I'm going to define the fundamental neighborhoods of 0. And the fundamental neighborhoods of 0 are just defined by a finite subset of the semi-norms. So I'm going to declare that by definition a fundamental system of neighborhoods of 0 will be so sets of the form U alpha 1 alpha n colon epsilon 1 epsilon n. So this is the set of vectors x in E, such that for each semi-norms here p alpha j of x is less than epsilon. And here you have alpha 1 alpha n is any finite subset of the indices defining the semi-norms. It's a finite subset of the collection defining the semi-norms. So in other words, when you have a norm space, you have a unique norm, and you introduce the corresponding balls. Okay, so if you have a norm, you consider the attached balls. Of course, they might not be exactly round. So it's a small neighborhood of 0 is just a ball. This is a fundamental system of neighborhood of 0. But here I may have semi-norms which will give you so p alpha 1 of less than epsilon 1, and then I can intersect with another family, but so p1, sorry, p1 of x, and here it would be another p2 of x less than epsilon 2. I'm going to, and then you might have the third one, even thinner, and then I'm considering just this. Now this will be the neighborhoods of 0. And now that I have the neighborhoods of 0, I can define what is an open set. So an open set is just so U in E is open if for every x in U there exists a fundamental neighborhood of 0, V, say V, or maybe I should put V instead. Well, V comes from French actually, voisinage. Say V such that well, the corresponding neighborhood of x is x plus v, of course, x plus v. Okay, and then of course I have no claim about separation, so I could just take p to be 0. Of course, if I take p to be 0, it's completely uninteresting. So if I take all semi-norms to be 0, it means that every vector satisfies this, and therefore you get the only neighborhood of 0 will be the full space. So of course you have a totally non-separated the row topology. This is uninteresting. So usually you want E to be separated, and for E to be Hausdorff. So E is Hausdorff. Well, it's the usual definition of a topological vector space. And it means that there is only vector 0 for which all semi-norms are 0. Okay? But then you have several semi-norms. So it's equivalent to say that x is equal to 0 is equivalent to the fact that for all semi-norms, P alpha of x is 0. Well, it's mostly this implication that is interesting. It's the other one. The other ones. Okay, and usually you assume this. So you assume separation, but not for a single semi-norm, but for the collection of semi-norms. And for instance, when you have a vector space, you always have so-called weak topology. I'm going to use it. So the weak topology of a vector space it's a strange topology. It's a strange topology. So you take E star to be the dual, and you define the collection of semi-norms to be simply for each linear form E star. You take P phi of x to be the absolute value of phi of x for all the semi-norms. It's the algebraic weak topology, so it's usually not very useful. The algebraic topology. Usually completely useless. But what is called a weak topology, if E is already a topological vector space, so if E already has a topology, you might be interested in the topological view, so the continuous view. So this is more interesting. So if E if E is already a topological vector space, so E prime will be the topological dual. So it means the algebraic linear forms that are actually continuous with respect to the given topology. So this is a subset of E star of continuous linear forms. And then something that is more interesting is the weak topology with respect to E prime. So you are going to take the semi-norms, but only the semi-norms that actually are already continuous with respect to the given topology. Okay, so you take then the family of semi-norms. Those ones. Where phi is in E prime. So this is called the weak topology, and it is actually a weaker topology than the given topology you are starting with. So you are starting with the topology, and now you are obtaining a topology that, of course, has somehow bigger open sets, because these, if the P alpha are continuous, these sets are going to be open with respect to the topology you are starting with. So you are going to get, for the weak topology, sets that are open already for the previous topology you were starting with. So you get a new topology, but in general, it's not the same as the one you've been starting with. It's weaker. You have less open sets. So this is why it's called the weak topology. So this one usually you disregard because it's usually very bad. It exists, but it's very bad. So this is a weak topology that is of interest. Okay, now an observation is that, well, of course, something that is very interesting is when you have a complete space. So you may have been told of what is a complete metric space, but here you don't necessarily have a metric space, okay? Because I don't have a unique norm, so I don't have a unique distance. But you still have a concept of completeness. So you say that so I'm going to consider one can, if you look at Dolbeault-Grothendieck, for instance, you will be introduced to very abstract topological vector spaces that are not even definable by semi. So I'm not going to consider this. I'm going to consider only those which are defined by semi-norms. And Dolbeault-Grothendieck shows that they are actually the ones called locally convex. Locally convex because actually when you consider semi-norms, what you get is convex sets. And if you take intersection of convex sets, you get convex neighborhoods of zero. And there are very strange topological spaces where the neighborhoods are not even convex. So this is considered by Dolbeault-Grothendieck, but I will not do that. And actually, it can be shown that topology is definable by semi-norms if and only if it's locally convex. You heard about that? Well, that's very abstract general stuff. I will not do that. Okay. So, so now let us consider. So I will call this a locally convex, according to what I explained, a locally convex topological vector space. just the same for me as a vector space together with the topology defined by a family of seminoles. With topology defined by a collection of seminoles. So then you can define completeness. Well, completeness is that well, unfortunately, it's not necessarily metrizable. So you need should I do this? Of course, if you consider sequences, it's not enough to define completeness. But if you have a sequence, it means that it's convergent if and only if it satisfies the Cauchy criterion for each P. So you have not just one norm, you have several norms. So a Cauchy sequence is a sequence that is that satisfies the Cauchy criterion for each P. So I will do only this because actually I'm going to consider only those which are metrizable. So in fact, there is a slight difficulty that if you don't have a metrizable space, Cauchy sequences are not enough to define completeness. So again, look at Dolbeault-Grothendieck. I don't want to look at this very general. So let me stick to Cauchy sequences. Okay, xk, k in n is called the Cauchy sequence. If so, for every seminorm and every epsilon positive, then there exists an index n such that for all indices pq larger than n, then p will be used. So for every mn, then p alpha of xn minus xn is less than epsilon. Definition as usual, except that you want it to be true for every seminorm. And then you say that E is, well, you say sequentially complete if every Cauchy sequence converges. Definition. E is sequentially complete if every Cauchy sequence is convergent. And the other definition of completeness, which I will not give you need filters. At some point in French education, it was introduced at the last year of high school, definition of general completeness, which I think was crazy, but turned out to be done 14 years ago when Dolbeault-Grothendieck was ruling in French education. So anyway, I'm going to consider only those ones which can be defined only by countably many. So the very important fact is that if the topology can be defined only by countably many seminorms, then actually your space is metrizable. So observation. If can be defined by a countable family of semi-norms then the topology is metrizable. So metrizable means that you can find a distance that defines the topology. Metrizable means can be defined by a unique distance. And the topology which are separated, which was Hausdorff. If Hausdorff. Assume that. You assume the topology is Hausdorff. Then topology is metrizable, i.e. definable by the distance. Okay, so proof. Suppose you have a countable family of semi-norms. So now I'm indexing just by the integers. Well, the finite case is very easy. So let's do the countable case. So you have a countable family of semi-norms. And you assume that this is Hausdorff. So then I'm going to define the distance. So distance of x to y. Admittedly, it will be a strange distance. I'm going to take sum over alpha of 2 to the minus alpha times the minimum of 1 and p alpha of x minus 1. And you will easily check that this satisfies the properties of distance. It's Hausdorff because it can be 0 only if all p alpha are 0, but I assume that my space is Hausdorff, so all p alpha 0 implies that x equals to 1. So this is going to be a distance. So this is a distance exercise. And now I claim that this distance defines the same topology. So of course it's translation invariant. It's translation invariant because if you add the x plus a and y plus a, of course, so this is, it is translation invariant. Namely, if you compute distance of x plus a and y plus a, it's equal to distance of x a for all vectors x, y, a, e. And therefore, I only have to check that the neighborhoods of 0 are the ones we want. So what are the neighborhoods of 0? The neighborhoods of 0, so you simply say that d of x0 should be less than epsilon. It means that the sum of d2 to the minus alpha minimum of 1 and p alpha of x should be less than epsilon. But of course you have a series here And for alpha large, anyway, this is less than 1. And so when 2 to the minus alpha becomes very small and even negligible with respect to epsilon. So I'm only saying that the ones that are before that step are small. So this, of course, this implies, so it means essentially that P alpha of x is less than 2 alpha epsilon for the small, for a range of alphas, but then for alpha large, you have no condition, because anyway, whatever is P alpha of x, because of the 2 minus alpha, it will become less than epsilon. So actually, requiring this only requires that a finite subfamily of the seminorms are small. So it's exactly what I defined to be the neighborhoods of 0. So you have exactly the same neighborhoods of 0 as the ones I defined by the definition. So I leave the rest of the argument as an easy exercise. So this means this just for a finite subfamily. Okay, and then then it's easy to see that Cauchy sequence then for this family is the same as the Cauchy sequence for this distance. And then you have the usual concept of a complete metric space. Okay, and now a fresh space, by definition, a fresh space is a space for which the topology is metrizable. Actually, you can show that the topology is metrizable if and only if you can find a countable family. Well, anyway, you assume this, and it's complete. So definition. So a fresh space. So this comes from the French mathematician André Fréchier, who actually introduced this in 1925. A fresh space is a topological vector space whose topology is defined by a countable family of seminorms, where topology is defined by a countable family of seminorms. That is Hausdorff and complete. Well, the important property is completeness. Hausdorff and complete. And therefore, it's in particular, but from what I have said, it's metrizable. So the topology can be defined by just. This is a counterexample. If you take E to be a Banach space of infinite dimension, if you take a weak topology, it will not be metrizable. This is a counterexample. The weak topology is not a question. I will not use that. So now let me come to the holomorphic functions after these definitions. So let us come back on Earth. So you have O of omega and this family of seminorms Pk for all compact subsets. So a priori, compact subsets do not form a countable family if you have more than countably many compact subsets. But you don't need to consider all compact subsets. You need only to consider an exhausting sequence. So you could take all semi-norms, but it's not needed. You have the same topology if you only consider those ones. For instance, you consider K mu to be the set of points in omega such that, say, the norm of x with respect. So I usually denoted the simple norms by only one bar, because in this course we will have double bars are more complicated norms. So I will leave the double bars for more complicated norms, and simple bars for usual Euclidean norms, Hermitian norm. I will denote by simple bars. So this is in any norm on Cn. For instance, a Hermitian norm, usual Hermitian norm. Okay, and less than nu, and then I want the distance, usual distance in Cn of x to the complement of omega is, say, larger than 2 to the minus nu. Okay, so suppose you have an open set like this. So it may be unbounded. So suppose you have 0 here. Then you take the points that are not too close to the boundary, and then you cut. So the distance here should be larger than 2 to the minus nu, so not too close to the complement. And then it should not be too far. So it's at most at distance nu here from the origin. Of course, this is a bounded and closed subset, and therefore compact. Bounded and closed and compact. And now I claim that this is an exhausting sequence. Exhausting sequence means that any compact set is contained in one of the k. So for every compact k in omega, there exists nu such that k is contained in k nu.
Is nu a natural number? Or?
And nu here is just natural numbers. Well, the proof is very easy. Actually, this exhausting sequence has an additional useful property that it's strictly increasing. So k nu, if you just replace nu by nu plus 1, of course, you will allow points that are a little bit closer to the boundary, that are a little bit farther from 0. And then you have that k nu is contained in the interior of k nu plus 1. And now it's easy to see that the union of the interiors, so the interior suddenly contains the points that are strictly less. Interior of k nu certainly contains the set of points that are of norm strictly less than nu and at distance strictly larger than 2 to the minus nu. And the union of these, of course, is equal to omega. Omega Because if you take any point x in omega, it will be less than some integer, and the distance will be larger than some positive number, therefore larger than some 2 minus. Okay? So this, if you take the union of all, you can get the whole open set. And now, if you take any compact set, of course, it's contained in this countable union of open sets, but by definition of compactness, it has to be contained in a finite subset. And therefore, in the one that has largest index. So this is what you call an exhausting sequence of compact sets. And now I claim that it's enough. It's enough to define the topology. It's enough to consider the k nus. You don't need the whole compact sets, because as soon as k is contained in k nu, of course you have that pk is less. You take the soup of the function here, supremum of the function over k, and of course it's less than pk nu. So now if you consider the set of functions pk nu less than epsilon, it will be smaller than, so if you take pk nu of f less than epsilon, this is going to be smaller than pk f, set of f such that. And therefore, you don't need that one, because you are taking intersection. You want the fundamental system of neighborhoods of 0. So what you want is the small ones. So since you want the small ones, you don't need that one, because anyway, that one is smaller. So in that case, you don't have a countable family of seminorms, but if you restrict yourself to those seminorms, it defines the same topology. So topology is actually defined. So topology of O omega can be defined by the pk nu in natural numbers. And now it's well known that it's a complete space, because if you have a Cauchy sequence, it means that you have a sequence of holomorphic functions that forms a Cauchy sequence on every compact set, and therefore, well, it's easy to check that the limit is holomorphic. You refer to the original theorem, you apply in one variable or whatever, so it's a complete space. Okay, and therefore, it's a precious space. It's a theorem. You can restrict to those. It's quite and actually, in the sheet that I have distributed, it is shown that you can never define the topology by a single unit. So it's not a Banach space. You cannot define the topology of O omega by a single unit. It's impossible. Okay. So remark, by exactly the same argument, if you consider spaces of, say, ck functions, space of ck functions, well, it's real in that case. So you take omega in Rn, so
this is the space of CK functions. So what can you take as semi-norms exactly? So the semi-norms, when you have CK function, what you want is convergence of all derivatives on uniformly on every complex set. So the semi-norms that you are going to use are the PK, maybe put M. P. P. Define PKQ, you are going to define the soup over all the points in K of the maximum over all derivatives of order x moves Q of the d alpha. In that case, for a CK function, you need to take the soup of the derivatives because convergence of the function don't imply convergence of the derivatives. And it's again a fresh space exactly for the same reason, because you can restrict the compact sets to be an exhausting sequence of compact sets, and the alpha, the Q anyway is a countable index, so it's again a fresh space. The fact that it's a fresh space is a standard theorem on limits of differentiable function. If you assume that all derivatives converge, then so this is also a fresh space. And it's enough to take the PK into Q. Or you could take C infinity as well, and then of course, in the case of CQ you fix Q, and in the case of C infinity you take all possible values of Q. It's again C infinity. So here you vary only mu, but for C infinity of course you vary as well Q. Again, question. But for holomorphic functions, of course, an important fact, which I have not shown, but I leave as an exercise, is that if you have a holomorphic function, then it's a converging sequence, then all derivatives converge. So the derivative is a continuous operator on the space of holomorphic functions. D alpha 1 alpha n over dz1 alpha 1. So any operation, any derivative operator from O of omega into O of omega is continuous. Is continuous for the Fréchet topology. Of O of omega. I think I would not prove it. It just follows very easily from the Cauchy formula. Well, maybe I prove it with only one mark. So okay, so you apply the Cauchy formula. So you have the distinguished boundary here, FW over product of Wj minus Zj. And now I'm differentiating with respect to z. So I can just differentiate under the integral sign. The only thing I have to differentiate is zj. So what I'm obtaining here is that
you get a formula for the derivative, which is just so if you differentiate over z1, you get z1 squared, and then you get z1 cubed, but then you have factorial alpha j coming in because and then you will get the formula alpha factorial. Well, factorial of a multi-index is the product of the factorials. So you factor alpha here, and then here you're going to get in multi-index notation w minus z to the alpha plus factor. So this is the formula. And therefore, if you have a sequence of functions that converges uniformly, then from this integral representation, it's very easy to see that the corresponding intervals will converge uniformly. And by the way, you get the so-called Cauchy inequalities. Cauchy inequalities, which are very useful. So if you compute at the central point of the polydisk, the absolute value at the central point C0, then you take this is less than factorial alpha over 2 pi to the n, and the integral of f of w, absolute value, but then here z is the central point, and you are integrating on the circles, so each of these is equal to the radius to the alpha plus 1, but then you integrate on those circles, and the length is 2 pi. Okay, so so it's going to give r to the alpha plus 1 in multi-index notation. And then here it's the length element of the circle, so it's going to be r1 delta 1, rn delta n. And then the integrals over the angles are going to give you 2 pi, so the 2 pi to the n will cancel. So you integrate with respect to the circle, so you integrate in theta 1 theta n. So the 2 pi will cancel, and the r1, rn are going to cancel the factor. So what you get is that the derivative d alpha of f at z0 is less than alpha factorial over r to the alpha times the supremum of f on the boundary, on the distinguished boundary. Okay, and for instance, well, this will prove, of course, what my claim here about the continuity of this operator. So if I take the soup on I compute pk of d of f, okay, so what I'm doing, so if I compute the seminal pk of d of f, I have a compact set, but then I need to apply possibly a boundary point here on some polydisk that is a little bit larger. Okay, so I do have to slightly enlarge the compact set, because if I happen to integrate at a boundary point, of course, there is no way I can stay there. I have to integrate in a small polydisk and say that I'm taking the radii here to be epsilon. So I'm going to obtain something like alpha factorial over epsilon to the alpha. And then I have to compute the maximum distance. The maximum distance would be like by Pythagoras theorem, like square root of n times epsilon. So the formula would be this. Of f, where I denote k delta to be the set of points z in omega that are at distance at most delta of k. So my radius here is epsilon, so the diagonal is possibly square root of n times epsilon, if I'm using the Euclidean. Or if you are using the soup norm, well, something else. And of course, it proves the continuity for the Fréchet topology. Okay, now a important fact is Montel's theorem. I will conclude simply the topology here. Paul Montel is somehow my mathematical grandfather, because he was the PhD thesis advisor of Pierre Lelon, who was the PhD advisor of my advisor. Okay, so yes. Long time ago, anyway. So it's again in the 1920s, even earlier probably. Well, it's the same as in one variable. If you have a bounded sequence of holomorphic functions, then you can extract convergent subsets. And bounded means bounded on every compact set. So take an open subset then if f nu is a sequence that is bounded, uniformly bounded on every complex subset. That is, for every k compact. So I will to abbreviate. This means commutation compact. The double inclusion, well, means related compact. But implicitly, when I write k without otherwise explaining, I mean that k is compact. Double inclusion means compact or related. So for every compact, there exists this constant ck such that for every nu, well, the sup over k of f nu is less than ck. Okay, so there's a constant that depends only on the compact set, but not on nu. Then you can extract a convergent subsequence. And there exists a convergent subsequence F nu P, some infinite sequence. In space of homomorphic functions. So I only have 30 seconds left. So what is the proof? Well, the proof is essentially based on Ascoli's theorem. Okay, because if you have a bounded sequence, the first derivatives are going to be bounded as well on every complex set. And because the first derivatives are bounded, they are uniformly continuous, they are uniformly Lipschitz. So then by Ascoli's theorem, if you have a sequence of functions that are uniformly Lipschitz with the same constants, well, the constants are valid only on the compact set. Okay? The constant might explode when you approach a boundary, but when you stay far away from the boundary, say on this compact set, it's going to be Lipschitz with the same constant. And therefore, by Ascoli here, you can extract a convergent subsequence on K, but then you can have the so-called process of extracting a diagonal subsequence. So you do it for each K nu, and then I don't know if I have to make this precise. So you use a diagonal sequence, okay, plus diagonal subsequence technique. And you will get it. So of course it works also for C infinity. The same is true for C infinity. Because for C infinity, you assume that it's true, you have a bound for all derivatives, of course. So if you assume that all semi-norms are bounded, then you can take the semi-norm corresponding to the next Q, the higher, and then it will be true. But if you take a fixed CQ, for Q fixed, it doesn't work. Okay, so this is what I define what is a Montel space in the sheet. So I have a formal definition in an arbitrary vertical vector space. So omega is what is called a Montel space. C infinity is a Montel space. CQ of omega is not. So, well, it's just a reformulation. This is the Montel space. So the precise definition is given in the sheet. The Montel space is a space where the bounded sets, the closed bounded sets are compact. Bounded means bounded in this sense. For instance, a finite dimensional space is Montel. Of course, it's well known, and it's one of the first things you learned about compact sets. In Rn, a compact set is compact if and only if it is closed and bounded. It's true also for holomorphic functions. So in the space O of omega, being compact is equivalent to being closed, unbounded in this definition, in this space. It's true also for C infinity, but not for CQ. Stop there. Remark. C infinity is also Montel, but not CQ for Q finite. Okay, I've already run out of time, so Up there. So today I will give, so we don't have enough material, so I will give 3 lectures actually, and we will have at least one session next week.